Hello, and welcome to this presentation, Getting Started with NRT Directional Power Sensors. In this presentation, we'll explain the basic functions and operation of Rohde Schwarz NRT series directional power sensors. This presentation assumes a very basic understanding of RF power and directional power measurements. If you're unfamiliar with this topic, or if you'd like more in-depth information, the presentation, Understanding Directional Power Measurements, might also be of interest. Rohde Schwarz NRT series directional power sensors enable inline, simultaneous measurement of forward and reflected or reverse power. Similar to a thermal power sensor, the NRT can measure average or RMS power regardless of signal envelope or modulation type. The sensor's excellent matching and low insertion loss means that it has minimal influence on the measured signal and can be left in line during normal system operation as well. There are two NRT models. The NRT Z14 covers the frequency range of 25 MHz to 1 GHz, and the NRT Z44 covers 200 MHz to 4 GHz. Maximum power for both models is 120 watts average and 300 watts peak. The sensors can be operated from an attached NRT2 power reflection meter or from a PC using a USB adapter. Measurements supported by the NRT include average power, peak power, crest factor, CCDF, mismatch, and burst power. In the remainder of this presentation, we'll explain the basic operation and function of NRT directional power sensors. Let's start with a basic connection diagram. The NRT is connected in line between a source of RF power and a load or sink that absorbs that power. A host interface cable is used for controlling the sensor and retrieving measurement results. An arrow on the unit itself indicates the direction of forward power, with reflected or reverse power being power flowing in the opposite direction. The host interface can connect to either an NRT2 power reflection meter base unit or to a PC running the virtual NRT software. The features and functions of these two control methods are generally the same, and therefore in this presentation, we'll concentrate on how NRT sensors are used with the NRT2. The NRT2 is a hardware base unit that can connect to and control a single NRT power sensor. It has a simple user interface that displays measurement results both numerically and graphically, and it allows for easy configuration of measurement parameters. The rear of the unit also has a pair of B and C connectors for analog output and trigger in. In addition, the NRT2 enables remote control or automation using standard SCPI commands over LAN, USB, and/or GPIB, and remote GUI control using VNC. The NRT2 is operated using a touchscreen, as well as control and navigation hard keys. The preset key can be used to reset the NRT2 to its default settings, and zeroing is started using the 0 key. Other commonly used keys are the screenshot and manual trigger keys. And finally, the sensor is connected to the input jack on the front of the NRT2. The rear panel contains the trigger in and analog output connectors. We'll cover these in detail later in this presentation. It also contains the remote access interfaces, namely Ethernet, USB, and GPIB, and these can be used for remote control or test automation. Now let's look at the main NRT2 measurement screen. The connected sensor is shown at the top of the settings pane, which displays basic configuration parameters. The type of measurement for each direction is selectable on the right, as is the unit used for forward measurement. Underneath the settings pane are the measurement panes, which display the forward power and reflected power, both numerically and in the form of a bar graph. The forward measurement types include standard measurements such as average or RMS power and peak envelope power. Crest factor is simply the ratio of peak power to average power. CCDF, or the complementary cumulative distribution function, is a statistical measure which shows the probability of power exceeding a defined threshold. Burst average applies to bursted or pulsed power, and this is the average power scaled by the ratio of burst period to burst width. We'll discuss this again later in the presentation. And finally, the absorption measurements are simply the difference between the forward and reflected power. That is, they report the power absorbed by the load. Here are some examples of different forward-powered measurement formats. We have a peak envelope power of approximately 34 watts, shown numerically and as a bar graph. Switching to average power, we see a much lower value of about 3.1 watts. As we would expect from these numbers, the resulting crest factor, the ratio of peak to average, is quite high, with a value of almost 21 dB. The most basic reflection measurement is the level of reverse or reflected power. This is used together with forward power to calculate mismatch measurements, such as standing wave ratio and reflection coefficient, both of which are unitless, as well as return loss, which is measured in dB. And finally, reflection ratio is simply the ratio of reverse to forward power, which is reported as a percentage value. In addition to numeric values, measured or calculated values can be shown both numerically and in blue bar graphs in the main display. The scale, that is, the upper and lower limits of the bar graph, can be set in two ways. The first is automatic scaling, which uses the currently measured values to determine the appropriate measurement range. The second is manual scaling, in which the upper and lower limits are defined by the user. Note that a small display of currently measured values is shown in the upper right corner of this dialog to assist in setting appropriate values. In addition to absolute measurements, as shown here, the NRX can also display relative values. These are indicated by rel in the results screen. Relative measurements are values that express the difference between the measured forward and reverse power and the user-defined reference values. There are two ways of defining these reference values. The first is by manually entering a numeric value and turning relative measurements on. The second is by using set to set the currently measured values as the reference. Note that the bar graph displays will also change to show relative measured values. The final basic configuration parameter is limits. Upper and lower limits can be defined for both forward and reflection measurements, and these limits are indicated by red lines in the main results screen. Limits are defined by tapping to the right of the settings pane and then enabling and defining the upper and lower values. If a limit is exceeded, a large red bar will indicate this in the measurement results screen. A limit violation can also be reported via one of the NRX's external interfaces. We'll cover this towards the end of the presentation. Now that we've covered basic operation, let's talk about some additional topics or parameters of the NRT. These are zeroing, defining the measurement direction, setting the measurement frequency, applying an offset, triggering, filtering, which includes averaging and video bandwidth, burst measurements, and the use of the rear panel input-output connectors. Zeroing provides a more accurate measurement by removing offset voltages from the analog circuitry in the NRT. This process is very simple. With no power present at the sensor, press the zero hard key and then the zero button to begin the zeroing process. This only takes a few seconds. Zeroing is recommended in 4 cases: when the temperature is changed by more than 5 degrees, when the sensor has been removed or reinserted, when more than a day has passed since the last zero, and when very low-level signals are being measured. Measurement direction is set from channel configuration. In the default auto mode, the highest measured power is interpreted as the forward power. The use of automatic direction is therefore not recommended if forward power and reverse power are roughly equal. Direction can, however, be manually configured with the ports numbered as shown. The user can then select the direction of the power, 1 to 2 or 2 to 1. Like most power sensors, the NRT is not frequency selective. This means that it measures all power within the sensor bandwidth. However, a frequency value is shown on the NRT measurement display, and the reason for this is that setting the measurement frequency allows the sensor to correct for its own frequency response. After entering the measured signal's frequency in channel configuration, the NRT's internally stored correction values are applied to both forward and reflected measurements. Entering a frequency value will therefore provide the highest accuracy in measurement results. Offset can be used to adjust measured values to compensate for attenuation between either the source or the load and the NRT sensor ports. For example, here we have a source of power of 10 dBm and 3 dB of cable and/or connector loss between the source and the NRT. By entering this 3 dB offset, the NRT will display the true source power of 10 dBm rather than the measured value of only 7 dBm. The default behavior of the NRT is to measure continuously, but measurement can also be configured to begin only when a trigger event occurs. There are 3 trigger modes. In normal mode, a measurement is made whenever a trigger occurs. In free run mode, measurements are made continuously. And in single mode, the NRT makes only a single measurement when the first trigger event occurs. The source of the trigger can be the input power itself, or it can be a signal present at the trigger-in connector on the rear of the NRT2. Note that it's also possible to manually trigger the NRT using the one trigger hard key on the front of the NRT2. Filtering refers to 3 parameters. The first of these is video bandwidth. The choice of video bandwidth will affect the measurement of peak envelope power and derived quantities such as crest factor and CCDF. Video bandwidth should be set to the smallest possible value, normally 2 to 3 times the measured signal bandwidth, since this reduces the effect of noise on the measurement. Integration time defines the time period over which a single power measurement is made, and averaging mode and count defines how many readings are averaged into one measured value. Using a higher averaging count will lower noise, but will also increase overall measurement time. Burst power measurements show the average power during the on period of a bursty or pulsed signal. The average burst power can be determined in 2 ways. In automatic mode, the sensor detects the duty cycle, or percent on time, of the bursted power, and calculates average burst power from duty cycle and average power. In user mode, the user manually defines the burst width and the burst length of the input signal. The last topic we'll cover is the input-output connectors on the rear of the NRT2. These are configured by pressing the system hard key and choosing I/O. The first connector can output an analog voltage signal in the range of 0 to 2.5 volts. This voltage is proportional to either a user-defined range of forward or reflected power, or it can be used to signal a limit violation in either direction. The second BNC connector can be used for a trigger-in signal, or as a second analog output for either forward or reflected power. Let's end with a brief summary. Rohde Schwarz NRT directional power sensors are able to make simultaneous measurements of forward and reflected or reverse power, with results being presented in a variety of formats, including average power, peak envelope power, CCDF, etc. Mismatch or impedance matching measurements such as SWR, reflection coefficient, and return loss are also automatically calculated. The NRT can be connected to either an NRT2 power meter or to a PC using a special USB adapter. Both relative measurements and limit lines are supported, and the NRT also implements numerous additional features and measurement configuration parameters. And finally, the NRT provides external input-output connectors and enables remote control using VNC or standard Skippy programming commands. This concludes our presentation, getting started with NRT directional power sensors. If you'd like to learn more about RF power measurements or power sensors from Rohde & Schwarz, please see the links in the video description. Thanks for watching.